So I have just a few announcements before I turn the show over to the speaker for today. So if you have any suggestions for future topics or speakers you would like to see at this tutorial series, please email them to me. You can find my address in the top right side of the slide. If we did anything well today, or if there's anything you think we can improve on, please use the QR code on the left side of the screen to send us anonymous feedback, and we can try to make sure we keep doing the things we're doing well or make changes to things that we need to improve on. If you want to follow along with the slide and codes for today, scan the middle QR code on the screen. That will take you to a GitHub, and the materials for today will be under the folder that starts with today's date and the title being APIs. If you are not already a member of GDS, scanning the QR code on the right side of the screen will take you to the page where you can join for GDS. If you are already an APS member, then joining the GDS topical group and getting access to many resources in data science for physics beyond these tutorials is only a $10 extra charge. The next tutorial for this series will be in 2 weeks on Friday, June 6th at 1 p.m. Eastern Standard Time. The title will be Evaluating the Limits of the Physics Learned by a Machine Learning Model, and this will be by Ashley Dell, who is a postdoc at the University of Toronto. We have had 4 tutorials already, all of which have been recorded, and the videos are posted on YouTube. If you want to view the recordings for the past tutorials on things like supervised machine learning and an introduction to data science, you can use the left QR code to view the recordings through the GDS Engage page, which is the website provided by APS, or the right QR code to view the videos on YouTube. The left QR code will also take you to the website where you can register for all the future tutorials in the series that have already been scheduled. Finally, new this week, GDS will be having a paper highlight series. We'll be accepting papers from GDS members, and then we will highlight them on our website and on our social media platforms. And so if you have recently published a paper in a peer-reviewed journal that you think deserves to be shown to the GDS community, please scan this QR code and fill out the form, and we'd be happy to reach out to you and see how we can help promote your paper. And so with that, I will stop sharing and turn it over to our speaker.
Okay, let me share my screen first. Okay, so thanks, Julie. Everybody can see my screen? Yep, okay. So thanks for the introduction and thanks for inviting me to give this tutorial. So today I'm going to talk about probably a bit different from what the other tutorials have covered. So the other tutorials are basically how to do machine learning when you have a set of data. Here I'm going to talk about something a bit different, is how you actually access training data. So especially training data that's in online databases. So there's a lot of training data. So you might have some of your own data you want to fit machine learning models to, but there's lots of other databases that are online that you can download data and then try and do machine learning on. Okay, so some of these databases. So first, I'll start by just going through a few slides just to give some background, and then I'll switch over to the Colab notebook. But just to start, so to give some background, there's a lot of materials data that's now available online through websites and programmatically accessible APIs. So this includes both experimental data. So this is something that's sort of only becoming available now. It's still relatively scarce. Often these databases are, you need to subscribe, you need to pay to access these databases. While computational data has been online for a while now. So most of these databases are like 10 plus years old at this point. So they're sort of mature. The data is relatively plentiful and the data is freely available. So some of the experimental databases that do exist, so there's this materials platform for data science. So this is a commercial database. It's kind of expensive. Then there's this another one for it's specifically experimental materials property data. So things like the superconductivity database is available at this materials data depository. So this is a Japanese database. I think this is this National Institute for Material Science. So they have a lot of databases data on things like superconductivity and so on. They don't necessarily always have structural data, so it sometimes can be a bit problematic when it comes to training APIs, training machine learning models. So some other crystallography data. So for crystallography data, for structural data, there's the inorganic crystal structure database. So this also requires purchasing a license. And then there's a free open access database, which contains kind of similar data, which is called crystallography.net/COD. So this crystallography open database is also available. So this one is data inside is free. So then some of the major computational materials databases are things like the Materials Project Database, the AFlow Database, OQMD Database, Materials Cloud Database, this Materials Project Descriptor Database, the Nomad Database, which is kind of an aggregator database and actually contains quite a lot of data from these other databases that are included within Nomad. And then there's this common API for materials data called Optimad. So today we'll be looking in a bit more detail at the APIs and how you can access data specifically from Materials Project, AFlow, and Nomad, as well as how to use this common API Optimad. And that's basically more or less what we'll focus on today. Again, most of what we're going to focus on here is specifically materials data, but again, a lot of the basic concepts of how to use APIs are pretty much transferable. And so if there's other database other data repositories containing different types of data, you will also be able to use some of the skills you learn in this tutorial, hopefully to also be able to access these other types of databases. So for computational material, so first though, to do a background on how this data is actually generated. So how we do what's called automated computational materials discovery. So typically what we do is we start from either experimental structures, so things that have already been observed, or what we call structural prototypes. So these are basically underlying crystal structures, things like, for example, the rock salt structure, so the sodium chloride type structure, and then you decorate this with different elements. Then you do calculations, usually at the quantum mechanics level, usually with density functional theory. So packages such as VASP or Quantum Espresso are generally the most popular ones. These are then piped into one of these databases that I described earlier. And then you can basically interrogate this database. You can basically search for candidate materials, or you can use the data to do things like training machine learning models. So the way these codes are then automated is basically you have some kind of a wrapper package, either a computer program or maybe something that's more like a set of Python scripts that wrap around this DFT code. You basically start from automatically generate the required input file. So you basically just give it what kind of structure and what elements you want, and it will generate all the required input files. It runs the DFT calculations, monitors the DFT calculations. If it detects an error, it changes the input parameters, and so it restarts the calculation. So try and get it to run to converge. If it runs into a problem, so if everything converges successfully, then it can parse the output files, extract things like it can extract things like the electronic band gap. It can plot the full band structure in reciprocal space. It can along the high symmetry paths. It can combine results from multiple different DFT calculations to calculate, for example, the phonon dispersion, or it can calculate elastic properties, so bulk modulus, shear modulus, and so on. And then at the end, it formats the data and puts it into the database for online storage and dissemination. So something I mentioned a couple of times, and something that we'll come back to a bit later, is this idea of crystallographic prototypes. So the idea here is you start from different commonly observed crystal structures. So things like maybe the perovskite structure, the rock salt structure, the wurtzite structure, the Heusler structure, and so on. And then you decorate these by different elements to create these new hypothetical materials. And then you perform the calculations. And from these calculations, you can check then what the formation energy is. You can check whether this is likely to form or not. You can also calculate different properties of these materials, like the electronic structure or elastic properties, or so on. Okay, so there's a few different databases, and the first one I'm going to go through is this AFlow database. And to go through this, I'm going to switch over. I'm going to exit out of this presentation. So if you're following along, we can go to the and show. We're going to switch over to the Colab notebook. So again, as Julie mentioned, if you go to this 052325 APIs and look at this materials databases and APIs, the IPYNB, so this Colab notebook, you have this button at the top here, open in Colab. So if you click on this button, this will open this notebook as a Colab notebook, so you can actually go inside and read. So if you scroll down, you can see the first set, we have a link to the various different databases that we're going to be looking at. We're going to look at the first 3 ones. So if you click on here for the AFlow database, this will open up a link to the homepage of the AFlow database. So you have several different things that are available here. You have links to, AFlow seminars. So this is a list of seminars that they host. You have AFlow tutorials. So this is sort of similar online tutorials that have been posted on YouTube. So this shows the AFlow database, but also shows like the underlying AFlow codes, how you can generate your own data using AFlow and so on, and also perform data analysis. You then have, then if you scroll down somewhat, you'll see you also have different applications. So the main one we're going to look at today is this sort of AFlow search application. So if we click on this AFlow search, so this will open up, so this is sort of a mirror, but so you have to click on it twice, just because they've had some problems with their with the firewall, so they have to work around the firewall, but this will actually open up the search page. So then when you open up the search page, you'll see something like this. You'll see the periodic table, and you'll have this display button over in the corner. So this will toggle, so you can toggle either between this periodic table and between the property filters, or you can bring both the periodic table and the property filters up on one page, which is usually what I prefer to do. Okay, so let's say we want to do a search. Let's say we want to do something very simple. We're just going to look for sodium chloride. So you select sodium, chlorine, and then we have the number of species equal to 2. Okay, so number of species equal to 2 is quite important, because if we have more than 2, if you don't put in the number of species, so let's say we leave this blank and we hit search, we'll see that we don't just get sodium chloride, but we're going to get things like, well, aluminum, beryllium, chlorine, sodium, oxygen, silicon. So you see, you get all kinds of, you get everything that contains sodium and chlorine, but you also get everything else, any other elements that are possible. If we restrict to just 2 species, so just 2 elements, then we see we just get sodium chloride. Okay. We can also search for the electronic band gap. So we can do add electronic band gap. And then we can also set a range. So we can restrict the value. So let's say we want things with an electronic band gap between 4 electron volts and let's say 8 electron volts. So we can hit search. And here we have the electronic band gap. So you can see it ranges depending on the space group, depending on the structure, we get different band gaps. We can also do a sort here. So by clicking on these arrows, here we sort from smallest to largest. If we click sort again, so you can see we've got 2 different space groups here. So we've got 2 different structures. So this is the normal rock salt structure, normal sodium chloride structure. This is a simple cubic structure. So this is a different symmetry. And you can see you get a different electronic band gap. So you can sort by from largest to smallest. If we click the arrow again, sorry, from smallest to largest, now we got from largest to smallest. Okay, let me just check on that. Make sure I have covering everything. Okay. Okay, so some of the other information that we get here, you can see you've got the space group, you've got the Pearson symbol, and you've got the electronic band gap. And now we can do some more examples, and you can do various other examples. So if we want to look, say, search by, we want to do something with the symmetry, search for symmetry information, you can go to relax structure. So this allows you to look at different symmetry properties. So here we have what's called the AFlow prototype label. We'll talk more about this later on. But you can also get things like, let's see if I scroll down, if I can find it. Point group, reciprocal lattice. Space group. Okay, yeah, space group isn't here because space group is already inherently included. So if we would just want things with the rock salt space group, we can go 225 to 225. And then we can do a search again. And now we're going to see that we don't have the 211 space group here anymore. So if we sort by the electronic band gap, we see we only have ones with 225. Okay, so now we've sort of narrowed down the search again to have it return only the structures with a specific symmetry. So now we're going to switch back to the slides. I'm just going to show you, because we have a couple of exercises. So if you want to follow along, you can go to the AFlow website and you can try and do the same, do some other searches. So here are just two different example searches. So the first one is to find the electronic band gap of silicon carbide with the zinc blende structure. So space group 216. And then the second one is to use the AFlow advanced page to find the electronic band gap of gallium nitride with the Wurtzite structure, space group 186. And maybe, so if you want to participate, if you want to, once you find the actual band gap of this, if you want to try posting it in the chat, and then we can start seeing how people are getting along. Okay, so maybe let's wait, maybe let's give people 1 or 2 minutes to try this out. And so, and again, if you have any questions, if you run into any problems, you can just post a question in the chat. Okay, so maybe I'll just go ahead and go back so I can go to the website and let's go through this. So the first one is to find the electronic band gap of silicon carbide. So let's go up here. Here we can do it. We can clear. We want just silicon and carbon. So we've got species is 2. We have silicon and carbon. We want to know the electronic band gap, and we want to do it in this 216 space group. So we change this to 216. So we only return those values with 216. We're not going to do any restriction on the value. And we're going to do on the search. And you can see here we get electronic band gap. So this is the DFT band gap of 1.37. Note that DFT generally tends to underestimate the band gap. So this might not be the actual correct band gap, but it is the sort of the band gap for this particular that you get with this particular method. Okay, let's do something similar. We're going to look for gallium nitride. So gallium nitrogen, again, 2 species. This time we want the space group 186. And do a search. And here we get different values. So usually in the 1.91 to 1.92 range to 1.93. So this gives you an idea of how the band gap can vary depending on the convergence. So these are just going to be just numeric due to numerical noise, due to maybe slightly different starting conditions. It converges to the lattice parameters might converge to slightly different values. So you get some variation in the band gap depending on this. Okay, let's go back to the slides and let's continue on. Let's look at the other databases. Actually, let's just go straight to the online. Okay, so the next database we're going to look at is the materials project database. So that's a little bit different. So one of the things you have to do if you want to use the materials project database is you need to, if you want to use the materials project database, you'll need to log in or register. So in my case, I'm going to log in. But you don't necessarily need to log in directly. If you're already logged into, say, a Gmail account, you can just click on continue with Google/Gmail. And then you can basically, now you're logged in, you can start exploring materials. So you can look at the search page, or there's various other tools that you can use. But we're going to start with the search page. Start exploring materials. Okay, so there's some different things here. Again, here you're not necessarily restricting to only, you don't necessarily restrict the number of species, but you have different options there. You can restrict to only these elements, at least these elements, and then you can provide a specific chemical formula. So if we want to look for our sodium chloride, again, we can select sodium and chlorine. So now it will search for things with only these elements. But if you want to search for things with at least these elements, you can go back, you can select at least elements, and now you're getting things with sodium, cobalt, carbon, chlorine, and oxygen. But let's go back to just only these elements. Hit search. And now let's scroll down and see what information you get. So again, kind of similar to with AFlow, you get things like the chemical formula, you get the structural information, things like the space group symbol and the crystal system. So whether it's cubic, hexagonal, or rhombic, etc. Number of sites, so number of atoms per cell. This is the energy above Hull. So this is sort of a measure of the stability of the system. So if it's 0, that means that that's the lowest energy system at that composition. It's actually on the convex hull, so it's a bit more complicated than that. But it also means that it's lower than any linear combination of any other two possible compositions. So here you can see that pretty much all of these, both of these have the same composition. So this means that this hexagonal structure is 60 millielectron volts higher in energy than the actual sodium chloride, normal sodium chloride structure. Here on the right, we can see the band gaps. So you can see it's pretty similar to the values we were getting in AFlow. So we get about a band gap of about 5 electron volts, similar to what we saw before with AFlow. Okay. So we'll come back to the end of the materials project a little bit later on when we look at the API. But the other database we're going to look at is Nomad. So again, if you go back to the Colab notebook, you look at nomad-lab.eu, and this will bring up the Nomad database. So if you click here on the top right, you can click Open Nomad. And here you can see that Nomad is a much, much larger database. It has like of the order of 20 million different materials. Okay, so the thing about Nomad compared to the other two, though, there's a few things that are different. AFlow and Materials Project and most of the other databases we've discussed are all generated. Pretty much all the data is generated by one group. So everything is generated with and using one sort of wrapper code. Usually, it's pretty much always generated with VASP, using a specific exchange correlation functional, specific settings, all this. So all the data is kind of internally consistent. With Nomad, however, you can see you have different options down here for the method. So you've got density functional theory, you've got type binding, you've got GW approximation, you've got the Bethe-Salz-Peter equation, which is more for excited states, dynamical mean field theory, which again is higher again, and then EELS, which is actually experimental data, or maybe simulated experimental data. So you have a lot of different method types, a lot of different data that's coming from different sources. So again, if we do a search, let's say we do a search for let's do a search for sodium chloride, sodium and chlorine. Again, we have the option here to select only compositions that contain only these specific elements. So if we only want sodium and chloride, again, we need to click this button. And now we can go and look at the results. So again, you can see that these are calculated, these are coming from different groups. You can see who the authors are, which group is generating this calculation, this data. So if we go down, we can see that here they're using FHI AIMS. We've got data generated with VASP and so on. And if we scroll down somewhat, you'll actually see eventually, if you scroll down, you'll start to see data that's coming from AFlow, data that's coming from Materials Project, and so on. So again, if we want to go and restrict to a specific type, let's say we only want GGA data, and we only want, we can even restrict it further to PPE. And you can see again, now we're only getting DFT calculations. So you get data from VASP, you get data from Quantum Espresso, mostly that VASP, Quantum Espresso, and VASP. Okay, and again, now you can see that some of this data is coming from Materials Project. Some of this data is going to be coming from AFlow as well, if we search down further. Okay, I don't want to search all the way to the bottom. Okay, so this is how you would access. So this is just a sample of some of the different databases that are online, but that you can access just using a web browser. But now let's go back to the slides, and I'll just talk a bit now about how you actually would access this data programmatically. So this kind of web portals that I just showed you, they're fine if you just want to look for one specific material, just one particular entry. However, if you wanted to build like a large data set that you could use to train a machine learning model on, then you want to be able to download the data programmatically. And to do this, you would use what's called an application programming interface. So some of the different application programming interfaces that exist are this Materials Project API, the AFlux, which is for the AFlow database. There's AIDA for Materials Cloud, and there's the Optimad API, which is a common API to access multiple databases. So today I'm going to talk about AFlux first, then I'll talk a bit more about the Materials Project API, and then finally I'll talk about this Optimad Common API. So the basic idea behind these APIs is what's called a representational state transfer application programming interface. So this is a way to basically download structured data from a database. So what it does is in response to a client request, the API will transfer a representation of the current state, i.e. a current version of a section of database, to the client. So common used methods are get, to retrieve data from the server, and post, to post data to a server. And post can also be used, as well as to post data to a server, you can also post like a query to a server. So the way it starts is you have a client, which is basically your computer. You have the server, which is where the database is hosted. You send a GET request. So you have a query that's in a specific format. So usually in the form of a URL or URI, so a universal resource identifier. You'll send this query to the server, and the server will send you a response, and the response will usually be some formatted data. So usually the default is usually coming in what's these JSON files. So this stands for JavaScript Object Notation. It's very similar structurally to a Python dictionary. So if you can very easily import this into a Python and then essentially use it as a Python dictionary, and then you can access specific data inside this response object. So the GET request, it's submitted in the form of a URI, so a universal resource identifier. So you can either submit this, you can just literally just build one of these requests and copy and paste it into a browser, into the URL part of a browser. You can also, but that's just not that different from using a web portal. But the big advantage of this is that you can also submit this using this URL lib module of Python, which is what we'll be doing in this tutorial, or by using Unix utilities such as the wget or curl. Okay, so URI has the following structure. You have a server part and you have the query part. So the server part, you'll have a scheme. So this is the HTTPS. You have your server, so you have authority. This will be like the top level domain, or let's say the higher level domain. So this, let's say the materialsproject.org or aflow.org. Then you'll have some path that basically says on this web portal that you basically have that you're specifying which API you're querying. Then you have the question mark, and then you have the query. The query comes after the question mark. So at AFlux, the example will be this. So here will be the scheme. So HTTPS. This will be the authority, aflow.org. This will be the path, so the API/AFlux. So this is telling you that you're looking at the AFlux API. Then you have a question mark, and then you have the query. So you have the server, and you have the query. And then the query part, usually in the case when you're querying a materials database, It's basically materials keywords with associated value ranges to filter returned entries. So I'll just go through one quickly, just go through how the code is structured, the basic Python code, and then we'll start looking at the examples in the Colab notebook. So here we want to import JSON. So the first thing we want to do is we import the modules that we're going to need, particularly the JSON module, which is what we'll use to read the return data. Then we import the modules for URL open. So this is what allows us to submit URIs to a specific web address and retrieve the return data. Then we have our server path. We have our search query. Then we have our example URI. So we have the server part plus the query part. So this is where we submit the URI with the query. So we have our response so JSON loads. So this JSON.loads is going to take whatever is returned here and convert it into a Python dictionary. So then we have our URL open. So we submit the URL to the website that we're looking to, the particular database server that we want to contact. We're going to read whatever's sent back, and we're going to decode it using this UTF-8 decoding. Then at the end, we're going to print out our response. Okay, so then we print out our response. Okay, so specifically for the AFlux server, so we have our https://aflux.org/API/aflux. Then we have a question mark, and then our query is built up from what's called matchbook and directives. So the matchbook is materials keywords with arguments, and there's a full keyword list you can get available. So if you query this aflux.org/API/aflux question mark help, and then with properties, that will give you a full keyword list. Or you can also see the full schema. So this will also give you information like what units the properties are in, a description of the property, some details about how it's calculated, and so on. Then you have the directives. So directives are basically formatting instructions. So the most useful directives are generally the format, which basically tells you what format you wanted to return that in. So you have JSON. So if you don't provide any format, it's going to return a JSON file. Otherwise, it's going to return, otherwise you can also select return HTML. You can also return the sort of a plain text, a formatted plain text option that AFlow itself can read, and so on. Then there's this paging directive. So we'll come back to this a bit later on, and we'll see how, because we can do this for different codes. But this is basically, it returns how many entries per page. So basically how many entries it will return at a time, as well as the page displayed. So you've seen already that some of these databases are quite large. So in the case of AFlow, you have maybe 3 million materials. In the case materials entries, in the case of Nomad, you have something like 20 million materials entries. So obviously trying to return all 20 million entries in one query is going to might cause some problems. So then you can sort of page through. You can say, okay, I only want the first 20 entries or the first 100 entries. Then you want to say, okay, you download the first 100 entries, then you can download the second 100 entries, and so on. And we'll talk a bit more how to do this in a later slide. So then if we want to go how AFlux actually works, so you've got several different logical operators, and the operator scope can be both inter-property or intra-property. So I'll talk a bit more about how this works. So especially for the logic operators, I'll discuss how this works when we start doing some examples. So the first thing we have are these block operators that set precedence. So these are basically just parentheses. We have an AND operator that's represented by a comma. An OR operator is represented by a colon. A NOT operator is represented by an exclamation mark. A loose operator is represented by an asterisk. This apostrophe is used to denominate strings. So if you want to do a string matching search, you use this. And then a mute operator. So this can basically say that you can filter on a certain property, but we don't necessarily want to see that property in the response. So that's this $sign. So you might say some of these properties might seem a bit, so especially the comma and the colon might seem a bit counterintuitive. So when we'll see later on when we look at the Optimad API as a contrast, they use a bit more verbose commands, but there are sort of some trade-offs involved depending on what you want to choose. So but the advantage of using a single character for the query is that the query can be much more compact. So certain URI strings can only have there's sometimes limits on the number of characters you can put in a URI request. There's also issues with reserved characters. So certain characters have specific meanings within a URI string, and they will have to be escaped if you want to actually use those characters. And we'll see some examples of where you have to do this with the Optimad API later on. But for now, all of these are URI safe, so you don't have to do any fancy escaping. They also are just single characters, so they're relatively compact. So some examples of common keywords. So if you want to look for specific properties, and some of the ones that we're going to use are the species label, which usually corresponds to specific element symbols. N species, which is the number of different species. So if you want sodium chloride, you put sodium Na and Cl in the species part, and then species as 2. EGAP is the electronic band gap. Space group relax is the space group of the relaxed structure. And then aflow underscore prototype underscore label underscore relax is this sort of structure type, so this prototype label of the relaxed structure. And I'll talk a bit more about how that works a little bit later on when we do some examples. So if we want to look at some examples, so let's say we want to do sodium chloride or potassium chloride with an electronic band gap of at least 5 electron volts. So here we have species is sodium. So here we have our server. Our first keyword is species, and then within these parentheses, we set the sodium or potassium. So it evaluates this sodium or potassium first, and chlorine. So this will give you sodium chloride or potassium chloride. The number of species is 2, and a band gap greater than 5 electron volts. So the wildcard operator here, this loose operator or wildcard operator, can also be used to set value ranges. So if I put this wildcard operator before the 5, this means something less than 5. If I put it after the 5, it means so if I put it before the 5, it means all values up to and including 5. If I put it after the 5, it means all values from 5 and up. So in this case, we want things that are greater than or equal to 5 electron volts. Okay. So the data is returned in the JSON format, so JavaScript object notation. The JSON files can be converted and read in and converted to Python dictionary. So import JSON, and then our response dictionary will be JSON.load response. The results are sorted in ascending order of the first keyword in the query. So for example, if we want to sort in order of band gap, we will put EGAP first. So EGAP comes first, so that gives you this. Now will be sorted in ascending order of band gap. So we'll see the lowest values of band gap first, then next lowest, and so on. Okay, so let's look at the actual example code. So now I'm going to switch back to the Colab notebook. Okay, so here's my Colab notebook. If I scroll down, so this is all the stuff we've looked at already. And here's our first line of code. So now we're going to do import JSON. So first we're going to import the JSON library, and we're going to import the URL library. So I can run. Okay. Now, next thing we're going to do is to define our Aflow server and our Aflux API. So this is our authority and our path. And now we are going to have our code. So again, we're going to search for sodium chloride and potassium chloride. So sodium or potassium and chlorine, and print the response. So we're going to first we're going to print the query, the actual query that's assembled, and then we're going to print the response. So here's our query, is again sodium or potassium and chlorine. Number of species is 2, and our band gap, we want to have 5 electron volts or greater. Now we have our directives. So this paging directive, in this case, we're putting in paging 0. That means to return all entries. Then we build our summons. So this is matchbook plus directives. Okay, so let me run this. So here it's building the query response. So if you click on this link, so here's the list, essentially the results that are returned. So it's a list of dictionaries. That should be in ascending order of band gap. Well, no, it'll actually be in alphabetical order first, and then ascending order of band gap. So if we want to change this, if we put the E gap first, and now rerun it, you'll see that the order changes down here. Yeah. Okay, let me come here. Okay, so the order should change. You can also click on this link and go directly to, so you can also submit this link in the same way. And now you can see that this is a JSON file. So this is in one of the nice things if you use the Firefox browser, if you open a JSON file in Firefox, it will actually format it in this nice way. Okay. So let's say we want to parse this AFlux response, parse the JSON response. So instead of just looking at this JSON file, which is a bit difficult to read, let's say we want to print out the compound name, so the chemical formula, and the band gap. So the chemical formula is given by this compound keyword, and the band gap is given by E gap, which we already saw up here. So now write this. So now we're going to, so this is a list. So if we loop over each entry in the list, and for each entry, so each entry will be called datum, and datum is a dictionary. So then we pull out from the dictionary, you pull out the compound, the value corresponding to the keyword compound, and the value corresponding to the keyword EGAP. So we print this out, and you can see again that this is in ascending order of electronic band gap. So let's do another example. We want to look, now we want to do formulate a bit more complex search query. So you want to do elements, materials containing carbon, silicon, germanium, or tin, but not lead. So now we want to have something that contains carbon or silicon or germanium or tin and not lead. So again, this is or, this is and this is not. Okay, so here's an example of when we're talking about, one of the things I mentioned before is talking about species being inter-property and intra-property. So let's say we were also to add a band gap filter here. Let's say and E gap for it between, let's say, greater than 1 electron volt. So 1 star. Okay, so these are intra-property. So these are between different species. So yeah, between different elements within one keyword. But now I'm also putting an AND operator between the different keywords. Okay, so the AND operator can both operate within the keyword query part argument or between keywords. So that's what we mean when we say intra and inter property. Here I'm also using the paging argument, and we'll go through that a bit more detail later on. But we have basically what we're looking for here is the first page, 1 of 10 entries. So let's run this and see if we get anything. Okay, so here we start to get them, and you can see now that we've got something that has carbon, but not lead, something else that has carbon, but not lead, and here we can see the different band gaps as well. So you can see you got things, a lot of multi-component compounds. Okay. So next thing I want to talk about is pagination. So let me just bring up the slides again for a second. Okay, so within AFlow, we use this paging directive to control the page number and the number of entries per page. So this is useful if you want to limit the amount of data being returned at once to avoid overloading your browser or your computer. So page is the set of data returned at a time. Paging 0 in AFlux will return all data. Paging takes two arguments. So the first argument is the page number n, and the second is the number of entries per page m. So you've got paging, you've got the number of the page number, and the number of entries per page. So if you want to return the first page with 10 entries per page, this is paging 1, 10. If you want to put in a negative page number, so this will still give you the first page of 10 entries, but it reverses the sort order. So instead of having a band gap going from the smallest band gap to the largest band gap, it now switches around and gives you the largest band gap first. So if you want to find a material with, say, the largest bulk modulus, you can use these negative numbers to bring that material up first. And that's one of the examples we're going to do later on. Okay, so again, let me just go back to the Colab notebook for a second. And let's look at the pagination. So here we're looking at the first page of 10 entries. So here, actually, let's look at here we're going to look at the second page. So if we want to look at the first page of 10 entries, we would go 1, 10. We do the sort. And we print out the response. So you can see it's printed 10 responses. Let's say we want to do the second page of 20 entries, 220. We can hit run. And now you can see we have a different set of entries. If I was to reverse this, put a -2 in here, you'll see that we get a different set of entries because it's going to start in a different order. Okay, so it's doing the sodium chloride first because that's smaller band gaps, or because it's going to do first in alphabetical order. So it's doing sodium chloride first because sodium is after chlorine in the alphabet. N is after K in the alphabet. So it's listing these in alphabetical order. And then it's going to list them within this alphabetical order. You can see it's listing it in ascending order of the band gap. Again, let's reverse it just to see it again. So let's say the first page of 20 entries. Now we're getting potassium chloride first, and we're getting the largest band gap first. So we get potassium chloride, and now we're getting the smallest band gap first. So now it's in ascending order. Okay. Okay, so now I want to talk a bit more about structure searches. So this is one of the nicer things, one of the more useful things I think that AFlow has implemented recently, is this structure type search. So within AFlow, we have these what are called prototype labels. So for example, it has a specific format. First is the composition, so this anonymized composition. So in the case of perovskite, the anonymized composition is going to be ABC3. Then we have the Pearson symbol and the space group. So in the case of cubic perovskite, the Pearson symbol is CP5 and the space group is 221. So this is the simple cubic space group. And then we have the Wyckoff positions ABC. So this specifies this structure. There can also be additional parameters to do with things like, especially for, let's say, more complex structures, you have things like you might have like the C/A ratio. You'll have for every structure you're going to have a lattice constant and so on. But you don't necessarily need to use this for search. So let's say you just want everything that's the cubic perovskite. You can just search for everything that's a cubic perovskite by searching for things with this label. Okay, so some other examples. If you want to do it for rock salt, the prototype label is AB_CF8_225_A_B. And again, if you go to the AFlow website, I'll show you how to do this in a second, you can search for the prototype labels for different structure types. So let me just switch back over to the AFL website for a second, and we'll show you how to search for things. So let's say I want to get, let's say I'm on the AFL website. So if you go to the afl.org, you go to this prototype encyclopedia. You want to find a particular structure. So let's say I'm going to do zinc blend. I can hit search. And here I can bring up the zinc blend search page. And here we get the prototype label for the zinc blend structure. You can do the same thing with various other crystal structures. So let me go over to the Colab notebook and do this search by structure type example. So here I have a few different prototype label examples. So we have the one for cubic perovskite, rock salt, and zinc blend. And you can see more information on this. You can also look for Excel Finder. So you can see that this will give you an idea of how you can give a structure to Excel Finder. It will do the symmetry analysis and give you back what this prototype label is. And you can basically do a search then by structure type. So let's say we want to do an example. We want to search for sodium chloride in the rock salt structure. So again, this is the prototype label. So now we're looking for this prototype label relax. So this specifically the prototype label of the relaxed structure. So again, we'd have the same thing as we had before. We have species, sodium and chlorine, and species is 2. And we want to have it in the rock salt structure. So we're using paging 0 to return all the entries. And then we're using URL so open to submit this query. So I hit run. Then we get back our search results. So let's do something that people more likely might be wanting to try and do. So this is something that's people might be wanting to search for is lead-free halide perovskites with a band gap greater than 3 electron volts. So again, halide perovskites are often used in optoelectronic applications, so as photovoltaics. People might want to find ones that don't have lead, and they might be looking for a specific band gap for a specific optoelectronic application. So here we want to do halides. So we're doing fluorine or chlorine or bromine or iodine. We want to do lead free. So we want to do not lead. We have species as 3. And then we want to search for this cubic perovskite structure. And we want to have a band gap greater than 3 electron volts. So again, we can submit our search query. And we can retrieve our results. Okay, so then instead of putting in fluorine or chlorine or bromine or iodine, you can also search by groups of materials. So if you put in halogens as a variable in here, then it will search for anything containing halogens. You can do the same thing, for example, for alkali metals, alkali earths, and so on. And you should see once this returns the result, we should see that we get the same set of materials being returned. So again, you see the exact same thing. Get silver, beryllium, fluoride is the first one. And so on. Okay, so something else we might want to do is we might want to clean the data that we've returned. So let's say first thing we want to do is we want to look for different compositions in the silicon carbide system. And silicon carbide has a few different polymorphs that can exist. So you might have a lot of different structures that are present with the same composition. So we want to look at species, silicon and carbon, and species is 2. We want to return the band gap. So in this case, if we use the wildcard on its own without a number, that means that we're saying that we want only materials where this value exists. Okay, so the only materials where the value is known. So only return entries where the band gap has actually been calculated. And then we're going to say, we're also going to return the species label. So in this case, if we include something in the query, without actually including any argument. It just returns the value, so it doesn't filter on it, but just gives you the value. Okay, so then we're going to again submit our query, convert it into a JSON, convert the JSON object into a Python dictionary. And now we're going to print out the length of the Python dictionary so we can see how many entries are returned. And we're also going to print out, we're going to run through all the entries in this list of dictionaries. And we're going to print out the chemical formula, the electronic band gap, and the prototype label. So let me run this. Okay, so if we look down, we see 44 total entries in our response. But you can see that we have some duplicates. So for example, these 3 entries here, all have the same prototype label. They all have roughly the same band gap. These are basically the same material. You can see 2 materials here that are basically both zinc blend. If we scroll down here, you can see some more zinc blends and so on. So in this case, sometimes they're AC and sometimes they're CA. That means the switches on this, whether silica is on a site or carbon is on a site, are switched around. So now what we can do is we can say, okay, we take our dictionary that we've loaded and we only keep the entries with unique prototype labels. So we run through all the entries in our response. We have a list of silicon prototypes. So these are the ones, the unique labels. So we basically, the first entry we come is going to, by definition, going to be unique. So we added the label to this list, but then it's going to check the next entry it goes through. It's going to check if that entry, or if the prototype label corresponding to that entry is already in the silicon prototype list. If not, it's going to again, and we're going to keep that entry. Otherwise, we're going to skip it. Okay, and then we print out the final set of cleaned up results. So let me run this. So now you can see when we eliminate all the duplicates, we get rid of half the entries. And this is particularly something that's particularly useful to do when you're doing machine learning, because if you have a database where there's a lot of duplicate entries inside, if you fit machine learning model to that, the model is going to be skewed because there's some of the different entries are overrepresented. So you might end up having or not only that, but you might, when you do your train test split, some of the entries might be in the training set or also in the test set. So that's going to basically make the model look better than it actually is. Okay. Okay, so I don't know if anybody has any questions so far. Otherwise, we're going to run through a couple of practice exercises. So again, I'm going to put the practice exercises here. So the first one is to use the AFlow API to find the bulk moduli. So in this, what's called this Voigt-Royce-Hill approximation. So basically it's the bulk modulus in AFlow that corresponds to this keyword for materials that contain titanium in the AFlow database. So then a couple of questions is, what's the material with the highest bulk modulus? So we want to sort this in descending order. So we want to use a negative page number here. So what's the space group of this material? And is this material, is this a metal or is it an insulator? So EGAP type. The other thing we want to do is to use the AFlux API to find electronic band gaps. So EGAP for all rock salt structure material. Rock salt structure, so this, again, this prototype label, alkali halide, where we can use this alkali metals as our species arguments, alkali metals and halides as our species arguments. So how many of these materials can we find in the AFlow database? Okay, so I'll give people a couple of minutes to do that, and then I'll do the examples. Okay, so I'll start working on this. So the first thing we want to have is our matchbook. So our matchbook should have the species. In this case, we just want titanium. We want the bulk modulus, VRH, and we want the E-gap type. We want to see the one with the highest first. So we've got this paging minus. We build our matchbook and our directives. And we get our response. We print our response. Okay, so our species is titanium. The bulk modulus, we want to return all the values of, we want to only return materials where the bulk modulus has been calculated. So the bulk modulus workflow has not been performed for all the materials in the AFlow database. It's only performed for a relatively small, small fraction of the materials, because this is it requires multiple different calculations for each material. So that's why we want to include this in parentheses. We want to include this star. So we only want to see the materials where this has actually been calculated. And we want to get the whether this is a metal or an insulator. So then we can run this. Now we get our results. So first material here is titanium. If we really want to get the bulk modulus of the highest one, then we should really put this AEL bulk modulus first. So what happens if we do this? Do we get a different set of results? Because now, before this, it was listing in alphabetical order. Now it's going to list in order of bulk modulus. Okay, so now it's, again, you see, by changing the order that we put the keywords in, we're actually able to get a different order of the results. And now, because this is negative paging, it's going to list them in order of descending bulk modulus. So the highest value of the bulk modulus is first. So here we get this value, it's almost 300 gigapascals. So this is quite a hard material, as this iridium titanium alloy. Oops. Okay. So the second question is to find all the electronic band gaps for all rock straw structure alkali halides. So again, we build our query. We have our species is alkali metals and halogens. We have this is our structure. So we want to have rock salt structure materials, and we want to get we're going to also return the band gap in this case, because we want to find the electronic band gap. So we're going to return the electronic band gap for materials that actually have this calculated. So again, we're going to have our directives as paging. Copy this. Do a search. Okay. Well, we specifically wanted to see how many materials are returned. So let's print out the length of the response. So you can see here that it's returning alkali halide. So here's potassium bromide. We look at the next one. Again, these are all just potassium bromide, but you get the idea. So how many entries are returned? So generally, the second time you run the same query, it should run a bit faster, because usually there's some caching Sometimes it might take a bit longer though. Okay, so again, we get 19 entries this time. Okay. Okay, so let's move on. Let's keep going. So let's just quickly talk about the Materials Project API. So this is a little bit different. It uses what's called an MP RESTer. It uses the MP RESTer API. So again, this is something that's developed by Materials Project. So Materials Project is a bit different internally from most of the other databases. It uses what's called a document-based database, MongoDB. So the data is returned as document objects. It also requires an MPI key, which is an API key, which is related to your login or registration on the Materials Project website. So some of the most important keywords include these elements, which are the chemical elements present, N elements, so number of chemical elements present, band gap, so the electronic band gap, N sites, so the number of atomic sites, symmetry, so crystallographic symmetry information, materials ID, so Materials Project material ID, formation energy per atom, so this is the formation energy per atom, and so on. And again, you can see more details at this nextgenmaterialsproject.org/API. Okay, so the API Materials Project itself, it requires you to install this MP-API. So this is not something that's pre-installed within Colab. So you have to do this pip install. So exclamation mark pip install. So this is basically the exclamation mark is something that you're telling it that you're running a command line command within a Colab notebook. So if I hit this button here, you'll see that it starts running the MPI installation. So it will install the MP/API for this session of the Colab notebook. Okay, so now once that's installed, we need to import the Materials Project API client. So from MP_API.client, we import the MP RESTer. And then the next thing we have to do is we have to get our API key. So if we go back up to the Materials Project page that we've logged in on, so if you've logged into Materials Project, you can go to API, and this will give you your API key. So basically you can copy and paste this in here. So you should use your own API key. Generally, this is like something that's tied to your account. So you can hit run. Now you've basically created you've instantiated this MP RESTer object with your API key inside. And now you can perform queries to the Materials Project database, and it will basically, now if you use this MPR object, it will have your API key inside, and so you'll be able to access the Materials Project database. So to query it, you use this materials mpr.materials.summary.search. So then we have our elements, our silicon and oxygen, and then we're going to query for a band gap between 0.5 and 1 electron volts. And they're going to print out how many entries we get. Okay. So now we have 440 for 3 entries. And for every single one of these entries, we're basically getting all of the Materials Project data. But if we only want certain specified attributes, we can use this fields argument, where inside the fields, we include the different different properties we're interested in. So things like the volume, the cell volume, the symmetry, formation energy per atom, and so on. So here we set up the fields. We have the material ID. So this is the Materials Project internal ID that they use to identify a particular entry in their database. We have the band gap, formation energy per atom, formula pretty, and symmetry. So this is all we're going to return. So again, we get 443 entries. Now, if you want to extract data for a specific entry, the way we do this is we use this print MP data 0. So let's say this is the first entry, will be MP 0. And we can see we can print out the relevant data for that. So we have our chemical formula, we have symmetry information, so space group, point group, and so on. We have our material ID, we have the formation energy per atom, and we have the electronic band gap. If you want to go sort of run through entry by entry and pick out particular property values, we can again we can basically treat this like the same way we treat a list. So we do for entry in MP data, and then we print out entry.material ID and entry.band gap. So we print out entry dot the property we want to print out. So if we run this, you can see we're printing out the MP ID, materials project ID for this material, and we're printing out the electronic band gap. Okay, so let me. Okay, so that's sort of an overview of how you can use materials project band gap. Sorry, how you can access the materials project database using their API. And finally, I'm going to talk about the Optimad common API. So the rapid expansion of these materials databases and APIs, it creates issues with having to learn a new API for each database. So efforts are being made to implement common APIs and standards. So the this Optimad common API is an API developed by this Optimad consortium. So you can find out more information about them here at optimad.org. And the full current Optimad specification is available on GitHub. So materials-consortia/optimad/blob/master/optimad.rst. So there's several different databases that support Optimad. So this includes some of the databases we've seen already, like AFlow, Nomad, and Materials Project, but also databases like this new database called Alexandria, the computational materials repository that's based in Denmark, Jarvis that's hosted by NIST, materialscloud.org. So this is the same people who developed IEDA, and OQMD, which is based at Northwestern University in the US. And so this list of databases is being updated all the time. And the current full list is available at optimad.org/providers-dashboard. Okay, so like similar to what we saw before with AFlow, it supports several different logical operators. So the AND operator, the OR operator, and the NOT operator. You've got numeric and string comparisons. So things like less than, greater than, equals, less than or equals, greater than or equals, not equals. You have substring comparisons. So things like contains, starts with, ends with. And then you have list comparisons. So again, this is what you would use to check for elements. So this is has. So if you do a list of elements with has, that means anything that includes this, but also has more of it. That has all would be has just these elements. Has any would be like the or, has this or this. Has only would be has only these elements, and then length, we can say again the length of a list. So some keywords. So far Optimad is mainly focused on structure and composition searches. If you want to search for specific properties, you can search that on a database level. I'll show you an example of how to do that later on. But mainly the main two things that you can filter on right now are elements and the number of elements. So again, the list of elements and the number of elements. Optimad also has multiple different endpoints, so it's adding more now, especially for trajectories from things like molecular dynamics simulations. But right now, so the first two generated are called structures and calculations. So the Optimad URI is the following structure. Again, you have the scheme, authority, path, similar to Aflux. Then you have an endpoint. So this will be our structures or our calculations. Then we have our question mark, and then we have the query. So for example, if we want to do Optimad and AFlow, so if we want to search for materials containing titanium, you would do https://aflow.org/api/optimad/v1. Again, we're using the struct. So this is the server part. Then we have the endpoint will be structures, and the query will be elements has TI. So the full URI becomes aflow.org/api/optimad/v1/structures, and then the query filter equals elements has TI. Okay, so let's look at this example. We scroll down, we should see this example. So here we have our API. Now we set up our filter. So one thing to be wary of here is that one of the issues with the optimad method is that if you put in spaces or quotation marks, these are corrected. These are reserves in HTTP, and need to be escaped. So our space becomes %20 and our quotation marks become %22. So instead of writing filter equals elements has TI in quotation marks, we write filter equals %20 has %20, %22 TI, %22. So this is the full URI. So we can click on this URI and it should submit it to AFlow. And here we get the search. So we see that this contains things with titanium. So we can also submit this. And we get back a dictionary of a list of dictionaries. So here you can see, if we look here as well, you can see you have a few different high-level keywords. So you have the data keyword that contains all the data. You have the metadata keyword that contains things like the query you submitted, the name of the provider, all this sort of information. You have some links, which is sort of the link to the database that you just to the query you submitted. And then you have inside data is actually the list of all the different materials entries that have been returned. So if we want to see how many materials entries we returned, so print response. Here you get the 3. But if we want to see how many data responses, then we have to look inside this keyword data. So this basically now will be a list. And we see how many things are response. You see that we got 100 entries returned. So now we're going to do something that's a bit more complicated. We're going to look for materials that contain carbon, silicon, germanium, or tin, but not PB. So again, the same thing we looked at before. So we have, this time we have elements, has any, carbon, silicon, germanium, and tin, and not elements has PB. So you want any of these and not lead. So let's run this example. And again, you should see that we essentially get the same thing back as we got with, same set of materials back as we got with AFlux. Okay, materials project is a bit more complicated because again, you have to submit the keyword, but I'll just say the basic structure. So you have this MP optimad, this is the API, this is the filter. So just to look at some other databases, you can look at OQMD. So again, you can have oqmd.org/optimad/structures. So that's their server. And then we build the same filter as before, exact same filter as we used to query AFlow. And we should get their response. Yep, so we get a response from OQMD with exactly the same filter. We can apply exactly the same thing to Nomad. Okay, here we're going to do something a little bit different. We're going to look for materials that contain only titanium and oxygen. So this has only oxygen and titanium, but you could run the same query as before. So same query format. Again, you can query another database. Now, if we want with Nomad, we want to print out different elements. So lattice vectors and coordinates. So for entry and response data, so we're going to go into this data, this list that's designated by this keyword data in the response dictionary. So we're going to run through, we're going to print out the attributes and the elements. We're going to print out, so within this, again, within this attributes subdictionary, we're going to, for each entry, we're going to print out the elements, the lattice vectors, and the Cartesian site positions. Okay, so here you can see we get the elements, the lattice vectors, and the Cartesian site positions for each entry that's been returned. Okay, again, we can submit this more complex query that we submitted before for AFlow, and we can submit the exact same query to Nomad. Again, now you see that we only get 20 entries returned, so different databases set sort of a different default on the number of entries that they return. You can also look at database-specific keywords. So, if you want to search, for example, AFlow, you can do the same. You can use the same keywords as you used with AFlux to search for properties using Optimad inside AFlow. So this prefix is AFlow. So if it sees this underscore AFlow underscore before a particular keyword, it knows that this is an AFlow specific keyword. Any other database will ignore that keyword. AFlow will see, okay, this is an AFlow keyword. We take away the underscore AFlow underscore, and it looks for this AEL bulk modulus VRH. So again, we build our query. So elements has TI and n elements equals 2. And the bulk modulus VRH, the VRH bulk modulus is greater than 100 gigapascals. So we run this query. And again, we get back our results, list of results. Then the final thing we can talk about is Optimad pagination. So again, you can use Optimad pagination uses the following keywords. You've got page underscore limit. So this is the number of entries per page underscore number, the number of the page, and page underscore offset, so the number of entries to skip. So pagination commands come after the query, this question mark, but before the filter. So here, if we want to do page offset equals 100 and page limit equals 50, so we have our structures endpoint, we have our question mark, we have our page offset equals 100 and page limit equals 50, and filter equals elements has TI then after the filter. So here we're going to search Nomad for gallium. We're going to return the second page of 50 entries. So our page number equals 2, our page limit equals 50, and we want to have elements has gallium. So let's do our response. Okay, so now you see we return 50 entries, and we've returned a set of data from Nomad. Okay, so at the wrap up, there's a few exercises. I'm not going to go through them. I think we're running a bit low on time, so I'll just go through the exercises very quickly just to show you how to do this. And then we can wrap up. Okay, so the first exercise is to use Optimad API to find binary materials containing silver in the AFlow database. How many entries are returned? So let me copy this in. So here we have elements, filter equals elements has AG, and n elements equals 2. So we want to have silver, and we want to have 2 elements. And then we want to print the response, and we're going to also print the response of the data part of this list of entries that comes under the data keyword, because we want to see how many entries are returned. So let's run this. And now we see that we're getting back 100 entries. So let's now look at a different database. Let's look at Nomad. And we want to find materials that contain lithium but not sodium in the Nomad database. And we want to see how many entries are returned. So let's print the length of the response data. And then finally, we want to use the Optimat API to find ternary materials containing niobium in the Nomad database. So here we have elements has NB and N elements equals 3, so ternary materials. And then we also see how many entries are returned. So let's run this query. So again, it's the first set of 20 entries that are being returned. If you wanted a different set of entries, you'd have to return the page limit. Okay, so that's everything I wanted to show today. Let me just quickly wrap up. Just show the acknowledgement slides and mention some of the people who did the work on this. So the Aflux API was mostly developed by Frisco Rose, Marco Esters and Eric Gossett, along with Corey Oses and David Hicks. So David especially did a lot of work on the prototyping. And it's currently been maintained by Simon Dimilov and Hagen Eckert in the group of Stefano Curtarolo at Duke University. The Optimat Common API was developed by a large consortium. Gianmarco Ragnesi and his current postdoc Matthew Evans are some of the lead developers on this. Casper Anderson, Ricardo Armiento, and Saulius Kritsulis in particular were heavy contributors to the initial version as well. Materials project is developed by the group, mainly by the groups of Christine Persson and Anubhav Jain at Lawrence Berkeley National Laboratory. I think Patrick Cook is actually one of the main developers in their group. And then the Nomad, again, is developed by the group of Claudia Draxel at Humboldt Universität zu Berlin. I think Marcus Scheigen has been the most active member of her group in developing this. Okay, so thanks everybody for your attention, and thanks again for inviting me to give this tutorial. And if anybody has any other questions that they want to discuss, please let me know. So thank you.